right, today we're going to take a look at some special patterns when we factor trinomials. So what we're doing is we are looking at those special formulas that we learned in Chapter 9 when we learned how to multiply certain binomials, such as whenever we had when we were squaring a sum, or when we were multiplying conjugates, or if we were squaring a difference. And anytime we did that, we got a really specific looking trinomial as our answer. Well, since we're starting with the trinomial and we're going back to the factors, so we're kind of reversing what we did in Chapter 9, all of those special formulas will actually, if we can identify them, we can actually find a special pattern whenever we're factoring. So let's begin with talking about what a perfect square is. A perfect square is an integer like 36 or 121, and this integer can be expressed as the square, so remember a square is an exponent of 2 of another integer. So for example, 36 can be expressed or rewritten as 6 squared. 121 can be expressed or rewritten as 11 squared. It's the square of 11, or the square of 6 for 36. So when we have a product of a pair of conjugates, which we learned how to multiply in Chapter 9, what we get is a difference of 2 squares. So let's learn how to factor the difference of squares. So factoring a difference of square produces a product of conjugates. So you learned how to multiply the product of conjugates. So now we start with the answer, which is the difference of squares, and we know that if we were to factor the difference of squares, we end up with the product of conjugates. So for example, if we have x squared minus y squared, so these are two squares, right? There's an x squared and there's a y squared, and it's a difference because we're subtracting. So when we have a difference of squares, when we factor that, we end up with the product, which means multiply, of conjugates. And remember, conjugates means the same terms, but we have the plus, we have the sum, and we have the difference, okay? So notice that this is x, and this is x, and this is y, and this is y. These are the square roots of the squares that we were subtracting. All right, so let's look at an example. Let's factor x squared minus 49. So we can recognize that x squared minus 49 is a difference of squares because x squared is squared and 49 can be expressed as 7 squared. So now that we have a difference of squares, here is our first term and here is our second term, and we need to rewrite it as a product of conjugates. So we'll have the x plus the 7, and then we'll have the x minus the 7. So notice that we're using these terms here without the squares whenever we write our product of conjugates. The example is this, 5 minus 125x squared. So before we begin anything, I notice that I have a common factor in these two terms. I could factor out a 5. So when I factor out the 5, I'm left with 5 times 1 minus 25x squared. And this right here is a difference of squared because 1 can be expressed as 1 squared, and 25x squared can be rewritten as 5x squared. So now I have a difference of squares. So remember, a difference of squares factors to the product of conjugates. So I still have my 5 factor, but now I have the 1 plus the 5x, and then I have the 1 minus the 5x. I have the product of conjugates, and remember those terms are what are being squared in the difference of squares. Here's another example, 36x to the 6z squared minus 64y squared. So for this one, let's begin with factoring out any common factors. So I know that I can factor out a 4 because 4 goes into 36 and 4 also goes into 64. So now I'm left with 9x to the 6z squared minus 16y squared. So this is a difference, so I want to rewrite these in terms of something squared. So 3x cubed z squared is the same as 9x to the 6z squared. And then 16y squared is the same as saying 4y squared. So now I have the difference of squares. So now I can rewrite that as, I can factor that as the product of conjugates. So I still have my 4. Here's my first term, 3x cubed z, plus, here's my second term, 4y, and then I multiply that by the difference. So 3x cubed z as my first term, but this time minus 4y. Alright, so any binomial that is a sum of squares cannot be factored using real numbers. So we just did the difference of squares, which was a squared minus b squared. We're saying that even though we can do the difference of squares, we cannot do the sum of squares. It does not work. We cannot do a squared plus b squared. There is no special pattern to factor that. Now, if we are doing the square of sums, so the square of sums is different than a sum of squares. The sum of squares is you're adding two squares together. The square of a sum is you're adding them together and then squaring them. Now that does have a special pattern when we multiply. It's x squared plus 2xy plus y squared. So remember, in this chapter we're going backwards. So we're starting with this, and if we can recognize this pattern, then we know that when we factor it, it becomes this. And then also we learned the square of a difference, which is if you're subtracting and squaring, then we get this pattern, x squared minus 2xy plus y squared. And so since we're going backwards, if we can recognize this, we know that it factors to this. So the first and last terms have to be positive perfect squares. And that middle term needs to be twice the product of the square roots of the first and last terms. So if you see a problem where the first and last term are perfect squares, which means you can take the square root of them, and that middle term is twice the product of the square roots of the first and last term, then you know that you have either the square of sums or the square of a difference. So let's look at a squared plus 2ab plus b squared. So I have perfect squares for my first and my last term, and then I have 2 times the square root of the first and last term. So since I have that, I know I can rewrite that as the square of sums with the square root of the first term and the last term is what's being added. Now, here I have a perfect square for my first term and a perfect square for my last term, but I'm subtracting twice the square root of the first term and the last term, which means that I have the square of a difference. So I have the square root of the first term and the last term, and they're being subtracted, and it's being squared. That's how I would factor that. Let's look at this example. We have x squared plus 10x plus 25, and we want to factor this. Now, I recognize that this is a perfect square and this is a perfect square because the square root of 25 is 5. So now my question is the middle term twice the product of the square roots? So is it 2 times x, because that's the square root of x squared, times 5, because 5 is the square root of 25. So 2 times x times 5 is 10x. So it works. This is an example of a perfect square. So I want to write the square of sums. So I'm going to take my first term, and I'm going to the square root of my first term and the square root of my last term, and add them together and then square them, and that's how I would factor this question. All right, let's look at this example. 12x squared minus 36x plus 27. So the first thing I want to do is factor out that common 3. That we have a factor of 3 that we can factor out. And when I factor out that 3, I'm left with 4x squared minus 12x plus 9. So now I want to see, could this be one of my special patterns? Well, 4x squared is a perfect square, right? Because that's 2x squared. 2x squared makes 4x squared. So when I say 2x squared, I mean parentheses, 2x, close parentheses, and then squared, right? And then 9 is also a perfect square because the square root of 9 is 3. So now the question is that middle term twice the product of the square root of the first term times the square root of the last term? So 2 times the square root of the first term, so that's 2x, times the square root of the last term, so that's 3. Is that equal to negative 12x? Well, 2 times 2x is 4x, times 3 is 12x. So yes, that works. That means that this is a special pattern. So now that I know that it's a special pattern and I see that it's a subtraction, I know it's going to be the square of a difference. So I take the 3, which I factored out in the beginning, and then I'm going to write the square of a difference. So I'm going to write the square root of my first term, which was 2x, minus, because it's a square of a difference, the square root of my last term, which is 3, and then close the parentheses, and then write squared. And this is how you factor that trinomial. All right, next example, we want to factor out x to the 6th, y to the 4th, minus 8x cubed, y squared, z, plus 16z squared. So I don't see anything that I can factor out. So my question is, can the first and last terms be perfect squares? So let's see, x to the 6th, y to the 4th, if I were to square root that, I could do that. It would be x cubed, y to the 2nd. And if I took 16z squared and I square rooted that, then I would have 16z. So it works. So now the question is that middle term twice the product of the square root? So I said the square root of x to the 6th, y to the 4th was x cubed, y squared. So there's that. And then 16z squared was 4z. So 2 times x cubed, y squared times 4z does become 8x cubed, y squared, z. So this does work. So I know that it's going to be the sum of a difference. So now that I know that it's going to be a sum of a difference, I can rewrite it, okay? So I take the square root of my first term, which was that x cubed, y squared, minus the square root of my last term, which was 4z, close that parentheses, and then square it. And that's how I factor this example. All right, go ahead and try some problems on your own.